Okay, thank you very much for inviting me and giving me the opportunity to come and visit Bologna. I've actually been here quite a few times, and it's always a really great pleasure to visit Bologna and enjoying the city and what the city is offering and meeting people I know and here. I will talk about this concept of generativity or generative architectures, or more partly in general, and more specifically about generative eHealth architectures. And this concept of generativity, I think it's a powerful and very useful one within the area of eHealth and large-scale information systems or information infrastructures. The concept is coming from discussions related to the internet, and in particular how to regulate the internet. And the concept has been proposed and brought into a broad academic community by law professors. And I'll explain first a little bit of the background of the concept. And it's and sort of some of the lawyers engaged in the discussion about regulation of the internet were afraid that many of the proposals made would do a lot of harm to the internet. So sort of the question they have addressed is how to regulate the internet without destroying it and destroying what is important with the internet. And then I have to point out what has been important with the internet and which we should maintain. And the motivation for the regulation is, as I believe you know, it's then how to stop the legal distribution of copyright-protected material like music and movies, but also issues like the distribution of child pornography and lack of security has been one issue. But also related to this, the implementation of quality of service kind of thing, that you well, if you pay more, you get better service, and I can guarantee better service. And some of the lawyers have been worried that some of these proposals would do a lot of harm to the internet. And the kind of harm they would do, which we should, or what should be maintained, is the ability that the internet has demonstrated to stimulate new innovation continuously. And if you think about how internet is related to other infrastructural technology, and something which is quite close, ordinary telecommunication, fixed line telephony, it's I think you all see that the differences are quite remarkable. And if you take fixed line telephony, there was basically not any kind of innovation for 100 years. What you could use telecommunication technology for, as seen from the user's perspective, you could dial a number, speak, and hang up, period. That was what you could do, and the only thing you could use telecommunication technology for 100 years, from 1870 to 1970. And if you compare that to the last 50 years, the 50 years of the internet, the difference is enormous. And so what this discussion has been about is what are the critical issues, aspects of internet that has enabled this very different history of evolutionary trajectory, and what should we keep as it is in order to stimulate and enable this continuous innovation. So. And from the very early days of the internet, when I've contrasted the internet to telecommunication, the architecture of the internet has been pointed out as a very critical issue. And the architecture of the internet, as I said, was radically different from telecommunication technology. And this is described by this concept of end-to-end architecture. The internet's architecture is described as an end-to-end architecture. And what that means is that the intelligence, the functions of the internet are located in the ends, in the terminals. That means in the computers connected to the internet and not in the network. As opposed to telecommunication technology, fixed line telephony, everything was in the internet and almost nothing in the telephones. So and if you put lots of filters to stop the distribution of technology, or information you would not like to be distributed, like illegally copied music or child pornography. The proposal was to put filters and various technology into the network. So Larry Lessig is one very famous law professor now at Stanford, previously at Harvard, and he was arguing that it's very important to keep this end-to-end architecture. And if a lot of technology filters into the network, you destroy that architecture. So he is arguing that the end-to-end architecture should be protected by law in a way. Benkler is another, I'm sorry for all the spelling errors here. Benkler said that end-to-end architecture is another law scholar at Yale, I think. And he is arguing that yes, the end-to-end architecture is important, but that's not the whole thing. It's also the programmability of the terminals is very important. If the intelligence of fixed-line telephony was in the telephones, it didn't make much difference if we couldn't do any modifications to the telephone. So it's also the programmability of the terminals. So an important aspect of the internet, and various proposals related to trusted computing, for instance. They were worried that would also make the programmability of the terminals more constrained. And there are certainly examples of that. If you have an iPhone, for instance, if you develop an app on your own, to run that app, you have to upload it to iTunes, and you need a certificate. Apple is then checking that it's follow the rules, and if it does, you will get a certificate from Apple, and you need that certificate to run the app you have developed yourself. And if Apple don't like your software, they can invalidate this certificate and it's not running anymore. So this is also a kind of technology that will possibly do lots of harm to or constrain the programmability of the terminal. So it's both the architecture and the terminals that have made the internet such a powerful infrastructure and stimulated all and enabled all this innovation. So a third law professor, Jonathan C. Train, that he theorized this and come up with the concept of general capacity. That we need to have a more general understanding of these aspects. He says, and what has been behind the success of the internet is its generative capacity. And this end-to-end architecture and programmability of the terminals have given internet this generative capacity. But this is a concept which is then highly relevant beyond the internet, and I would say definitely to eHealth infrastructures. And what they're saying then is this discussion about what the internet has been and what it might be. The Citrain and the others, they contrast generative technology with appliances. And a typical example of an appliance is an old telephone or a refrigerator or that kind of things. It comes with certain features, and you cannot modify it. You have only those features that are provided, put into the technology by the provider, and you can now change to it. So what they're afraid of with many of these regulatory proposals is that the internet might turn into an appliance and lose its generativity. And this is how Citrain is defining generative technology. He says that technology's generative capacity is its overall capacity to produce unprompted change driven by large, varied, and coordinated audiences. And in a way, you might also read into this definition the open source community, which has been an important part of the internet, which is fit that sentence very well. And more specifically, it defines generative capacity as technology's capacity for leverage, what kind of good things it might be possible to make based on this technology, its adaptability, and its ease of mastery and accessibility. So this has a very strong focus on the technology and technology's capacity and technological features, even though the first sentence mentions audiences, humans, so it has also a human aspect, and there are some other scholars also using the concept of generativity in a different way. This is a concept of generative networks taken from an innovation theory professor. As far as I know, he's American, but he's a professor at Modena University. And he has developed a theory of innovation. And he's saying that the capability or capacity of a network of companies, actors, or a community to innovate depends on the generative relationships within this community. I will not go into the details of that, but what is important to have innovations, they are not coming from the technology proper. It also depends on the innovators, and it's this combination of the generative capacity of the technology and the generative capacity of the community related to the technology that matters. Talking about eHealth infrastructures, like all infrastructures, it's, as I see it, it's important to think about or taking into account and keep in mind that infrastructures have a different life cycle, evolves differently from how we, within the software engineering information systems field, about applications. Because the way we are thinking about it is that we ask the users, when the users, or we want to develop a new system, we ask the users what they need, what they want. We make a requirement specification, build a system, train the users, give them to the users, and then it's maintained for 10 years or something, and then it's replaced by another system. So it's this idea of design from scratch, and you design something new, and then you use it for some period and then replace it. Infrastructures are not like that. If you're thinking about the roads, they have always been there, and they're just modified, changed, and also the internet has been around for 50 years or something. So infrastructures are just evolving over time. So when we are developing a new kind of infrastructures, the way to do that is to modify and improve what we already have, to make it evolve in the directions what we want. So we need, generative infrastructures are then infrastructures that we are able to develop in the directions we want. And then we talk about different evolutionary processes. The first I point to here is the concept of bootstrapping, which is maybe a strange term, but it relates to the fact that infrastructures, like all standardized technologies, and how they are evolving is very much driven by network effects. And the more users there is on an infrastructure, the more value it offers to the users. Telephone networks, the more people you can, the value of a telephone or email infrastructure is not the functionality of the technology, but the number of users you can communicate with. And that means for the first users, there is nobody to communicate with. But as the number of users is growing, you are creating network effects, and those network effects make the value of the technology for the users larger. The more users are using it, so the evolution and the growth of infrastructures are very much driven by the network itself, by these network effects. But in the very beginning, there are no network effects. So that means to get, there is a takeoff problem. When you want to build a new infrastructure, it has no value for the first user. So how to get the first users on board and to start making network effects work to create these self-reinforcing processes. And that to come up with the first version we call bootstrapping, to bootstrap the network. And then adoption is that more users are using it. Scaling is that more applications, patient record systems are integrated with an existing infrastructure. Innovation is that new services are offered. Restructuring is that after some time we need to change it. So a generative architecture is an architecture that is supporting all of these processes. And one important aspect in talking about the relation link between the architecture and features of the technology and the community or the project developing it is there is notion of mirroring. Research demonstrates that always, everywhere, there is a strong link between the architecture of the technology, this is for all kinds of technologies, and the organization developing that technology. And those structures are mirroring each other. So there is a famous sort of famous law proposed by someone, I don't remember his name, saying it's going in one direction, that an organization is only able to develop a technology having the architecture which is mirroring the organizational structure of that organization. So this relationship between organization and architecture is important. And now I will give some examples from eHealth infrastructures in Norway. It's started in the late 80s, and after a couple of years, there was a private lab developing a very simple solution in 1987 for a transfer of lab reports from labs to general practitioners, which was extremely successful, and that triggered lots of activities and optimism about this kind of technology and interest. So lots of actors were gathering, hospitals, doctors, software companies, consultancies, and quite quickly there was reached a consensus that what was popular at that time was EDI technology, which is a kind of technology I think pioneered in the car industry. And the typical application of this technology was exchange of orders and invoices in the supply chain. And this technology was broadly becoming popular in the late 80s and seemed to be very appropriate here for the exchange of lab orders and reports, prescriptions, admission and discharge letters, and so on. So, and here is, I call this technology the EDI paradigm, and it was established as a dominant paradigm in Norway and many other countries, and things have changed, but they still have a very strong position. And the idea behind this paradigm is that you look at the information flow, the flow of lab reports and orders and so on between organizations, and then you assume that this information is a prescription, for instance. It's first the doctor enter the information into the patient record system, then print it and give it to the patient, or if it's a lab report, send it by ordinary mail to the lab, which is then entering the information into the lab system. So this, instead of that, you should just send the information in the document electronically between the applications. So the first illustration is in the information flow between the organization and institutions. And then they want to make eHealth infrastructure supporting this information flow where it takes place electronically, and then they come up with this architecture in the middle where the boxes are the patient record systems and the lab systems and so on, and they build this infrastructure by adding functions to the application for sending and receiving the messages. And then the next to the right is an illustration of the project organization developing this infrastructure, because when you develop the whole system by adding functions to existing applications, it's the vendors, owners of that application that have to do that. So then you need to involve all of them, and they need to agree on the information flow, and they agree on standards, and then they implement the required functionality. And this has not worked, or worked very poorly. And the problem with this, I would say, is partly the architecture, which makes the whole system a bit complex. But the main problem is the organizational structure and its complexity. And it's too complex to be able to build the infrastructures they want to build. And it requires too much coordination, and they need to agree about too much, and then everybody needs to do what they are promised to do and agreed upon. And it's a general issue that all these vendors have long lists of new requirements from the user base, what the user thinks is very important to improve here and now, and these projects are often not so important. So and that organizational structure, when you have decided on the architecture illustrated in the middle, the only possible project organization that can build this infrastructure is the one to the right. And it's too complex to build what they want to build. That's a short story. And then this is the Norwegian e-prescription solution, which is very close to that architecture. This is taken from a document. One important difference is a box in the middle, which is a central server database. So not all messages. And you can see there are 31 blue arrows there. They defined and standardized 31 messages as a part of this project. And you have the patient record systems to the left, which are exchanging lots of messages between the various other modules. So this is not exact, doesn't follow exactly or strictly this EDI paradigm, but it's very close. And when they started out with a focus on primary care and primary doctors and to work together with, primarily with the vendor having the largest market share for patient record systems for general practitioners in Norway. When they started, that vendor had 70% of the market and had 2 old systems and had just started developing a 3rd new modern one. And the functionality offered to the doctors was quite extensively. So that module, what I had to develop on new functions for the doctors was quite extensive and it would be expensive. So they suggested that they should develop this module just as a part of the new patient record system. And project management accepted that. I thought there was a good reason for doing just that. But then the problem was that that project was endlessly delayed because they were working hard, but the users didn't accept it. The functionality was, it was user interfaces, whatever, was not acceptable. And during the project, that company was bought by a German company, and the new owners, after 2 years or something, they were getting bored and fed up with the lack of progress. So they informed the project management that they were considering discontinuing the development of the whole system. So then this project was in deep trouble because that was sort of the so important part. If that vendor couldn't offer this, then there was not much help of the rest. So then they had to do something, and then they decided quite quickly, they were pretty desperate, to develop a generic module, a standalone module for doctors. And they did that actually quite quickly, and it was tested, and users were happy, and it was adopted. Later it was picked up by a hospital and adapted to use in a hospital as a sort of loosely coupled standalone module together with the dominant patient record system in Norway, and the vendor of that system was also all too busy to be involved in this. So the development of this generic standalone module was very much a quick fix, ad hoc solution to an urgent problem, but as I see it, it was a small but very important architectural change. And the change, the way this change matters was that they could ignore the vendor of the patient record system. It partly maybe reduced the technological complexity, but it reduced in a very important way the organizational complexity. So now the core project organization can develop that module and what had to be developed to start, for the users to start adopting this independently of those vendors. So now I'm running out of time, I think. There has been, this approach, EDI approach, has been very dominant in Norway, and it's the short story is that they have sort of failed. This e-prescription solution turned out to become, after a long time, a very successful infrastructure. But this architectural change was an important part of making it that success. But then there are a number of smaller but quite successful projects in Norway, which are not so much talked about or visible, but when looking at them, we see that they are based on a different architecture. And I'll not go into details here, but the main point is that they see the modules used by all users in combination. And and they are very loosely coupled to the applications used in the different organizations. And this is in more detail this lab report transfer solution developed by a private lab, and it was developed in 3 weeks by one person. And that programmer spent one evening together with a programmer from the vendor of patient record system having the largest market share, the one I talked about in the prescription case, one evening to do the required integration. And it was an instant success. And if you look at the relationship of the organizational structure and the architecture of the system, there is still mirroring. But in this case, it was just one person within one single organization that developed the whole thing. And the other successful projects we've seen in Norway, it's very similar to this. And also one important difference with these cases is that here there was an organization that decided first, we want to develop a solution having these features, offering these services. And then they asked, what kind of architecture makes that possible for us? So they decided on project organization first, and architecture was then a consequence of that. In this EDI paradigm cases, they decided on architecture first, and then the project organization was a consequence of that. When they had made the decision about that architecture, this was the only possible project organization. So one message is that you need to see this organization and architecture in combination, and it's the way it's a combination that matters. Then I will finish by adding some more detail. If you go back to the different evolutionary processes, this EDI paradigm that I said failed, the way it has failed is that it has basically failed to bootstrap. They were not able to come up with a working solution that the users could start adopt. So that it never took off. That has been the main problem. But then we have seen in other projects that when a solution, independent of the architecture for how it was developed, when it starts evolving, starts growing, adoption and scaling starts, actually this EDI architecture works quite well. But it does, but not for the bootstrapping process. And then we have seen in the e-prescription project where they had added some quite innovative new functions for multi-dose dispensing, that, for those of you that know what that is. And that is has been a quite ambitious and seems to be successful innovation and new functions offered to this. And then they also saw that this generic standalone module was quite important. So they used that until they come up with a stable solution that the users start to adopt. And then some of the vendors can, based on that stable, well-working specification, implement an integrated module supporting that functionality or an end system. So the conclusion then we see is that different phases need different architectures. And this EDI paradigm works pretty well for adoption and scaling. And then it's combined with also a different kind of organizational structure, while bootstrapping, innovation, and restructuring need a different architecture. And its community part is maybe the most important part. It is, these different phases requires, there are different kind of communities that are generative in the different phases, and those different communities to work to be generative, they need to be supported by different architectures. So there's a different combination of architecture and organizational structures that are generative in these different phases. Okay, thank you very much.